Hi, I'm Shanaz. We are going to begin this lecture by proving the path lifting property. Now, it is a result which shows the existence and the uniqueness of path lifting. But before we proceed further, let us recall what do we mean by a path lifting. So let us consider a map between spaces x tilde and x. So this is our map P, and suppose we are given a path from interval AB to space x. So this is the path F. Now let x tilde be any point in x tilde. So a path F tilde, this is said to be a lift of path F starting at point x tilde if F tilde of A is x tilde and this composition map P composite with F tilde, this is actually Fi if this diagram commutes. So now this x tilde is such that this F of A is P of x tilde. Now this F starts at P of x tilde and this F tilde starts at x tilde. So in that case we say F tilde is lifting of F. Now in previous lecture we have proved that if here we in place of this closed interval AB we have a space Y which is connected, and this P is a covering map with these conditions, then this lifting is always unique. Now in place of this connected space Y we have this interval AB here which is also connected. So this lifting is unique if this P is covering map here. So let us state this result here. So we have a theorem here. So it states that, so let us consider, let P be a covering map from x tilde to x be a covering map over the space x. Now by space I always mean a topological space, and by a map I always mean a continuous map unless otherwise stated. So these are conventions. By a space we mean topological space, and by a map we mean continuous map. So over the space x. So let F from interval AB to x be this be a continuous map. Let x tilde belongs to x be a point such that P of x tilde is same as F of A, then there exists a unique continuous map F tilde from interval AB to x tilde such that this f tilde of a, this is x tilde, and the composition map p composed with f tilde, this is f. So actually this theorem states that if p is covering map with these two conditions, so then there always exists a unique map. So uniqueness, we have already proved uniqueness in the previous lecture. Now let us prove the existence in this lecture. So proof. Consider a set, consider this set. So let us denote this set by S, and let us take all those points in interval AB such that there exists a lift of this restricted map, there exists a lift of this restricted map f when we restrict this on this interval to x tilde starting at, say, this x tilde. So this is the definition of this set. So a point S is in S if we have a lifting of this map, of this restricted map. So what we have to prove? We have to prove B is in this set. So we show that B is in this set S. Now one can note that A is in set S. Note that this set S, this is non-empty since A is in S. Now what does it mean to say that this point A is in S? It means that when we restrict F to this point A, which is same as the point F of A. So now what do we mean by a lift of this point F of A? It means if F of A is in point in space X, so this is F of A, so F takes this point here, so we must have a lift which takes this point to this space. Now it is given by definition that this is point A, this is F of A. So it is given that this F tilde of A is X tilde and P composed with F tilde is same as F. So that means A is in this set S. Now let us consider, let T be the supremum of this set S. Now since P from X tilde to X, this is a covering map, this is a covering map, that means this is X tilde, this is X. So that means if we consider any point here, so for this point we have an open neighborhood which is evenly covered by P. So now this P is a covering map. So for F of T in X, So obviously this is a point in X, because t is some point in this interval, so f of t will be a point in X. So if this point is there, we have an open neighborhood of f of t. So there exists an open neighborhood of, so there is an open neighborhood, say u of f of t in X, which is evenly covered by P. Now, as a reminder, by evenly covered, so this is open set U here, by evenly covered we mean P inverse U is actually a disjoint union of open subsets of X tilde, with the condition that each these open sets are homeomorphically mapped onto U. Now note here, so one can note here, so this is interval AB. So let us draw this a little bigger. So this is our space X here, and this is our interval AB, and this is the map F, which is a continuous map. And suppose we have a point T here, which is the supremum of this set. Now this is the point F of T, and this is the open set which is covering this point Ft. Now F is given to be continuous, so that means for any epsilon neighborhood there must exist an epsilon such that this neighborhood is carried inside this set U. That means there exists an epsilon such that t minus epsilon and t plus epsilon. So one can note here this epsilon neighborhood may contain some pointers outside P. So let us consider this intersection AB. So if we take its image, this must be contained in U. So let us denote this set by say JT epsilon. This is by the definition of continuity. So if we have a point T here whose image sits inside this open set, then we must have an epsilon such that this intersection, the F image of this intersection, sits inside U. So there, since F is continuous, there exists an epsilon positive such that F of JT epsilon, this is contained in U, where this JT epsilon, it consists of all those pointers X in interval AB such that this T minus epsilon is less than X is less than T plus epsilon, which is same as the set T minus epsilon T plus epsilon intersection with interval AB. So this is the consequence of this, of the continuity of F. Now since T is given to be the supremum of this set S, so this intersection over here, S intersection JT epsilon, this is non-empty because obviously T lies in this intersection, because T is in this set and T is in the supremum of set S. So choose some S naught in this intersection. Now if S naught is in S, then by definition of S there acts a lift, say neta naught, so then there exists a lift, say neta naught from interval A to S naught to X tilde of this restricted map AS naught starting at tilde X tilde. This is because S naught is in S, and this follows by the definition of S. So one can note here, so if neta naught is a lift of, so this is X tilde, this is X, and this is AS naught, so this is the map F restricted at this interval AS naught, and this is the left neta naught, this is what P. Now if this is the left, that means P composed with neta naught, this is actually F restricted at this point S naught. So that means P of neta of S naught is same as F of S naught. Now F of S naught is a point in X, so this is F of S naught, this is a point in X. That means this for this point in X we have a neighborhood U of X which is evenly covered by P, Now this F of S naught is same as this point, that means this point is evenly covered by P. I mean the inverse image of this point over here. So write this down here. So we write this down here. So since U is evenly covered by P, that means P inverse U is a disjoint union of open subsets of X tilde, each of which is mapped homeomorphically onto U, each of which is mapped homeomorphically onto U. So one of these open sets must contain this neta naught of S naught, because we claim here that this U which contains f of S naught, this is evenly covered by P. I mean P inverse of f of S naught, this is some point in these, is a point in some of these, in one of these open sets, but the inverse image of this point is same as inverse image of this point. That means when we take inverse of this point, now P being a homeomorphism, so that means neta naught of S naught must belong to one of these open sets which are evenly covering the open interval, open neighborhood U. So one of these points, one of these open sets must contain neta naught of S naught. The reason being P of neta naught of S naught is f of S naught, and this f of S naught is in X. So this is the reason that one of these open sets must contain this neta naught of S naught. So let this open subset be denoted by U tilde. Let this open subset of X tilde be denoted by U tilde. So one can note here, so we have proved here this thing. That means, so since f of JT epsilon, this is contained in U, implies f of X belongs to U for all X in JT epsilon. So let us pen this down here. So note that f of X belongs to U for all X in JT epsilon, and U tilde is homeomorphic to U via P. Therefore there exists a unique path. Therefore there exists a unique path, say lambda from JT epsilon to U tilde, such that lambda of S naught is neta naught of S naught, and P of lambda of X is actually f of X for all X in JT epsilon. Now let us understand this here. So what we do here, so this is the interval AB, and suppose this is the point T here, and this is the epsilon neighborhood. So this is T minus epsilon, and this is T plus epsilon. So this is our set, so this is our set JT epsilon. which is actually the set t minus epsilon t plus epsilon intersection interval AB. So this is space X here, and this is the open set U. So we have proved that this F takes this interval inside this U, because f of jt epsilon is contained in U, and this U is evenly covered via the map P. So we have proved that for each point in this, so this is actually the path here in this open set U. Now each point here is carried out to some point in U tilde, and given that this U tilde is homeomorphic to U, that means there must be a shadow of this path in U tilde. So this is a path in U tilde. This means that we have a map from jt epsilon. So we have a map which we have denoted by lambda from jt epsilon to U tilde, given by this diagram, that is P of lambda, P composite of lambda is F for all x in jt epsilon, and this lambda of S naught is same as neta naught of S naught. So S naught is some point here. So given this, we can define another map, but then given any S in jt epsilon, let neta from AS to X tilde be a continuous map, be a continuous path in X tilde given by, so let us define this. So we denote neta of X to be this path neta naught of X, where this X is from this X is lying between X and A and S naught. So neta is behaving this lifting, which is given here. So neta is this lifting, on this closed interval, and from S naught to S it is this lambda of X. So since this neta naught of S naught is same as lambda of S naught, so here one can note that this neta is continuous. So then this neta is a lift, then neta is a lift of this map. That means, so if neta is a lift of this map, that means this little s is in the capital S, thus this little s is in capital S. But we have chosen this s here, this s was chosen arbitrary point in this set, and we have proved that this s is in S. So this proves that, this shows that and this j of t epsilon is contained in S, i.e. this t minus epsilon and t plus epsilon intersection with interval AB, this is contained in S. So one can note here, but t is defined to be the supremum of S. So this containment is valid only then if this t is equal to B. Therefore, otherwise this is not valid. If t is not equal to B, then this contradicts the fact that t is the supremum of this set S. Therefore, it proves that t is equal to B and B is in S. Now if B is in S, that means hence there exists a lift. Now we are using the definition of S because B is in S, that means there exists a lift f from interval AB to x tilde of f there is a lift f from this of f starting at x tilde, so this proves the existence of this lift. And now as far as this uniqueness is concerned, just replace the domain space here, just replace the domain space in the previous lecture with this interval, then that would prove that this f tilde is unique. So this was the path lifting property.